Hello, and welcome to Lab 3, Calculating the Mass of a Black Hole, 62211. What is in this lab? This lab, we were given the data of a star's mass and its x and y position over time in the form of a CSV file. This star is circulating around a black hole, and the black hole's forces being the only one to act upon the star, causing it to orbit in a semicircular motion around this black hole. We need to use the data that we receive in the CSV file to estimate the approximate mass of this black hole using Python. By calculating this, finding the velocity over time, then converting to the momentum over time, and then to the F-net, and finding the F-net using Newton's law of gravitation to find the black hole's mass to be 4.15 times 10 to the 31st kilograms. First, we need to start off by setting some initial conditions. First, we can look at our initials position of the star, being 5 e to the 10th and negative 5 e to the 10th in the x and y position. Also, our star's mass being given as 2.43 times 10 to the 27th kilograms. We also need to set a delta t of 1 day, or 86,400 seconds, and our initial time being 0, as this is our first observation data point, as usual. Let's get into some calculations. First, looking at how we will figure out the initial velocity. As we open the CSV file, we'll iterate through it, being able to find the delta x by subtracting the next delta x from the delta x, the original coordinate, and then putting this delta x over delta t to find the change in the x component of the change velocity over time. We also can do the exact same with the y components to find the y's velocity. At the end of this while loop, we need to add delta t to t so we can iterate through the next steps. Some of our calculations continued is finding the velocities, the initial velocity and the final velocity. As we can use these initial and final velocity multiplied by the star's mass to find our initial and final momentum. When we can look at the change in momentum and put it into the change in momentum over change in time. This is because the change in momentum of change in time's value is the exact same as our F-net value, as we can see as we've placed right here. Also, we need to find out the direction of our momentum, or the p-hat, because to be a vector, a vector must have direction. We can figure this out by noting that the force over its magnitude is equal to its direction. We can use this then to find the parallel component by multiplying the d magnitude of momentum times the p-hat, and noting that this is also equal to its F-net. We can find the perpendicular component by knowing that perpendicular component of the force plus the parallel component of the force will be equal to the total net forces acting upon this star. This is also equal to its F-net. This value is also equal to its F-net value. Now, we might be getting a little lost in all these forces and velocities and momentums. So how do we actually calculate the mass of a black hole with all of these forces? We can figure this out by using Newton's law of gravitation, where the F-net, or what we found to be dp dt, is equal to the gravitational constant, 6.67 times 10 to the negative 11th, times the mass of a star, times the mass of a black hole, over the distance squared. We can manipulate this to find the mass of the black hole. We find that the mass of the black hole, using the equation below, is equal to 4.15 times 10 to the 31st kilograms. This is about 17,000 of the stars we are given. So what does this mean? Well, we can look at this as comparing F-net and momentum and how they compare to one another. While the values are the same, the meanings behind them are different. This is a very confusing concept to keep separated because we look at the values being very similar, but the F-net is actually the time derivative of momentum. While both of these have direction, momentum is not a force. We need to know the force components to be able to compare the forces acting upon the object in the system. Now, what if? Could we tell the difference if a new black hole was placed in the position of an old one, but the star's motion was unchanged? I determined not very likely. If the velocity is unchanged, then also the momentum is unchanged because our star's mass has remained constant. Because our momentum is unchanged, we will be viewing the same net force of our star from the original black hole. Since these are unchanged, we'd be unable to determine, even if there was a different mass of this black hole. To be able to see a difference in the mass of the black hole and tell that it was changed, we would have to see some sort of change in velocity on the star. This is partially what makes calculating these black holes' masses so difficult, because they are all done through models. Thank you, and now if you'd like to see, we can look at what my model actually looks like when it's run.